As we begin our look at substitution reactions, we need to step back and review what we know about Lewis acids and bases and expand on that knowledge. Gilbert Lewis was born in Massachusetts and educated at Harvard, spent a great deal of his career at Berkeley. And he's responsible for our notion of covalent bond and for those eponymous Lewis structures. You might be interested to see what Gilbert Lewis's original sketches of his Lewis structures look like. They were based on cubes, which later got refined into the structures that we draw now. So back to Lewis and the expansion of our definitions of acids and bases. So prior to Gilbert Lewis, the Bronsted-Lowry definition of acids and bases was the predominant way of looking at acid-base reactions and was focused entirely on the transfer of a proton from an acid to a base. But as Lewis refined his view of covalent bonds, he came to reason that you could expand that definition if you focused on the lone pair of electrons being transferred. And so you could encompass all of Bronsted-Lowry definition and many, many, many more reactions using his definitions. So by Lewis's definition, Lewis bases are species with an available electrons that can be donated to form new bonds, and Lewis acids are species that can accept those pairs of electrons. Since Lewis acid accepts a pair of electrons, it's called an electrophile, and that's the term that organic chemists typically use to refer to a Lewis acid. Lewis bases, by contrast, are donators of electrons, and they're typically named nucleophiles, meaning lover of nuclei, because it donates electrons to a nucleus with an empty or easily vacated orbital. And we're going to look more closely at those. Now, I should clarify some terminology here. When an organic chemist uses the term base, they usually mean a proton acceptor, a Bronsted-Lowry base. And when they use the term acid, they usually mean a proton donor, a Bronsted-Lowry acid. When the acid-base reaction involves the formation of a bond to some other element, especially carbon, organic chemists refer to the electron donor as the nucleophile and the electron acceptor as the electrophile. So just to separate things, acid and base involves proton transfer, and electrophile nucleophile involves a Lewis acid-base interaction of some sort. So there are many examples of Lewis acid-base interactions that you can find among chemical species, and these are a few of those. So fundamentally, Lewis base to an organic chemist, a nucleophile is something that has a pair of electrons that can be donated, and an electrophile is something that can accept those. So it could be kind of a traditional base with a non-bonded pair of electrons and a hydrogen ion. It could be a compound with a non-bonded pair of electrons and a substance that contains an open shell. You might recall from general chemistry that boron forms what are referred to as open shell compounds with 6 electrons around boron in an empty orbital. It could be a lone pair of electrons from an anion that is interacting with an antibonding orbital such that when the electron donation occurs, a bond is broken and resulting in a new bond formation and the loss of some sort of leaving group. And then we can also have typical Bronsted-Lowry sort of transformations, but again, these can be defined in terms of nucleophile, electrophile, where base donating a pair of electrons, acid with its acidic proton is acting as an electrophile. So throughout this chapter and throughout the course, we're going to continue to use the curved arrow formalism to show the flow of electrons, where electron pairs are coming from an electron donor to an electron acceptor. And it's important to get those curved arrows properly drawn so that they indicate what electrons are going where in the overall chemical reaction. So this is a type of substitution reaction we're going to talk about in more detail later on, involving a species acting as an electron donor, a nucleophile. Here, the specific electrons that are being donated are a non-bonded pair of electrons on this alkoxide ion. Those electrons are going to form a bond to this carbon, and that's going to cause the rupture of this carbon-chlorine bond in such a way that the electrons in that bond go to chlorine, so thus the second curved arrow. The result is that we've rearranged the electrons. This non-bonded pair of electrons becomes this new bond. This bonding pair of electrons becomes this new non-bonded pair of electrons on chlorine. So there's this notion of an electron flow from the electron donor to the electron acceptor. So that's our fundamental principle. Reactions happen when electrons flow between molecules. So a bond forms when the electrons move from a nucleophile to electrophile. And so in a more generic sense here, we often abbreviate nucleophile depending on whether it's a neutral and anionic species in this fashion, and electrophiles with an E depending on whether it's a neutral or a cationic species. So it's fundamentally important to keep track of the fact that nucleophile donates electrons, electrophile accepts electrons. Now you might say, well, why does this happen? Well, you can describe a lot of chemical processes. For instance, imagine the combination of a chloride ion and a hydrogen ion. Initially, there's an electrostatic attraction between those two things, but you form a covalent bond when they bond together. An organic chemist draws that with curly arrow designation, where we're saying, okay, where are the electrons going? Well, the electrons are coming from chlorine and they're going to hydrogen. The negative charge here refers to a non-bonded pair of electrons. The positive charge here refers to an empty orbital on hydrogen, and we get a new bond. So there are lots of different examples of the way these interactions can happen. So for instance, a nucleophile can have a lone pair of electrons in a non-bonding orbital, say the non-bonding pair of electrons on ammonia. The electrophile can have an empty orbital that's energetically accessible. Borane, BH3, because of boron occurs so early in the periodic table, has only a sextet of electrons around boron and an empty p orbital on boron. Then that can act as an acceptor of those electrons and allow the formation of a new sigma bond and a Lewis acid base complex. So again, using curved arrow formalism, we're going to say this pair of electrons on nitrogen is donated into that empty orbital, and we form that new bond. So the idea here is that there are orbitals that are interacting, and this is fundamental to the way we view these sorts of reactions. And in fact, it has a name. This is known as frontier molecular orbital theory, or frontier MO theory, that in order for a reaction to be successful, there needs to be overlap between the necessary orbitals. And in the Lewis acid base sense, there needs to be a bonding interaction between the electrons that are being donated and where those electrons are going to go. So there's a notion of a filled orbital and an empty orbital. There's also, if you think about that more deeply, you come to the conclusion that the molecules have to interact in a particular way, geometrically, in order for those orbitals to be accessible. So for instance, here, more with ammonia interacting with borane, the ammonia has to approach the borane in such a way that this filled orbital can overlap with the empty p orbital of the boron. If the ammonia approaches from the wrong direction, from the side, for instance, with it inverted, pointed with the non-bonded electrons pointed a different way, side to side here, none of these interactions would give rise to a successful reaction. It's only when the molecules have the proper orientation that the reaction can occur. Taking this idea of orbital overlap as essential for a successful reaction even further, we can think about this from a molecular orbital energy diagram point of view. So that's shown here for the interaction again of ammonia with borane, and that interaction being the filled non-bonded sp3 orbital on nitrogen interacting with the empty p orbital on borane. And that interaction looks like this. The empty p orbital would be relatively high in energy. You would expect that for an empty orbital. All the bonding orbitals would be much lower in energy. And the sp3 hybrid orbital on nitrogen would lie at some particular energy. The interaction between those orbitals would give rise to new molecular orbitals, both in a bonding and an antibonding sense, to form a sigma bond. And so we are forming a sigma and a sigma star. The pair of electrons comes from nitrogen. Boron is contributing none in this interaction. And so when the bond forms, that pair of electrons now can reside in the sigma orbital. And because the sigma orbital is lower in energy than either of these two, we get a net energy gain, a net gain in stability, and the reaction occurs. This energy diagram also leads us to some understanding about why some reactions occur and other occur quite readily and why other reactions do not. And we know from experiment and we know from calculations that for reactions to take place, the molecules first have to overcome their electronic repulsion by either a charge attraction or an orbital overlap. If you think about it, most molecules repel one another because they're covered in a cloud of electrons, and electrons are negatively charged. And so as the molecules approach, there is in fact an initial electronic repulsion. Now, that can be overcome if one of the species, for instance, is charged, or both of the species is charged. One is a cation, one is an anion. And then there's going to be an electrostatic attraction. But a lot of reactions don't involve charged species interacting. And in those situations, it's orbital overlap that allows for the reaction to proceed. The second thing is the orbitals have to have appropriate energy in order to interact. They need to be energetically accessible to one another. The filled orbital of the nucleophile and the empty orbital of the electrophile. And you can imagine different scenarios. You can imagine species interacting that have this sort of energetic relationship where the interacting orbitals are close in energy. You have the nucleophile supplying its pair of electrons. You have the electrophile with an empty orbital. The interaction produces new molecular orbitals and a net large energy gain, and the reaction occurs, and you get a new strong bond. You can imagine the formation of weaker bonds, where there's an energy disparity between the empty electrophile orbital and the filled nucleophile orbital, but nonetheless, the reaction can occur and you form a new bond. This might be a weaker bond than what's formed in the first example. And then finally, if the interacting orbitals greatly differ in energy, there can be a negligible energy gain and little or no reaction occurs because there's simply too large of an energy gap between the interacting species. This sort of interaction is known as a HOMO-LUMO interaction. Specifically, that refers to the highest occupied molecular orbital, the HOMO, of the nucleophile. That's where the electrons are coming from. It's an occupied orbital. There are electrons in that orbital. So this is the HOMO. It's interacting with the LUMO of the electrophile. Now the LUMO stands for lowest unoccupied molecular orbital. So this would be the first orbital above all of the filled orbitals in the molecule that is empty, unoccupied. So the lowest unoccupied molecular orbital is known as the LUMO, and that's represented by the electrophile's empty orbital. So the best nucleophiles have high energy occupied molecular orbitals. So that's represented here. All of the other orbitals in the molecule are filled and then has a relatively high energy occupied orbital. And the best electrophiles have a relatively low energy unoccupied orbital. That unoccupied orbital is close in energy to the filled ones and lower than all of the other empty orbitals. And so Lewis acid-base interactions from an orbital theory are thought of as HOMO-LUMO interactions, highest occupied molecular orbital interacting with lowest unoccupied molecular orbital. So this is our Lewis base, HOMO. This is our Lewis acid, LUMO. All right, so what kinds of species can be nucleophiles? Well, a lot of things. They simply have to have a pair of electrons that can be donated readily, and it needs to be sufficiently high in energy to interact with an electrophile. And you can see from this slide that there are lots of examples of things. You can have nucleophiles with simply lone pairs of electrons, like ammonia or amines, even water molecules for that matter, and alcohols, which are just derivatives of water. And so in these examples, the highest occupied molecular orbital is in fact a non-bonding sp3 orbital, so a lone pair of electrons on some atoms. Some nucleophiles are anions, and they have a full negative charge. They can be quite reactive. So halide ions, for instance, shown by this bromine here, or hydroxide ions. And you usually just draw those very simply as OH minus, Br minus. In those instances, again, the HOMO is a non-bonding sp3 orbital on one of these atoms. We're going to encounter many other nucleophiles. Here's another example of that, which is the cyanide ion. The nitrogen on a cyanide ion can be quite reactive, and that's an sp hybrid orbital that's filled with a pair of electrons. But there are other species where the electrons are not non-bonding electrons, that the electrons are in some sort of reactive bond. And we've already seen this. Carbon-carbon double bonds, you know, can act as electrophiles. We saw that in the reaction of alkenes with hydrogen halides and the reaction of alkenes with water under acidic conditions. In those cases, the highest occupied molecular orbital is the bonding pi orbital of those alkenes. And we're going to encounter other species. Borohydride ion is a reactive species, and it will donate H minus, where the sigma bond between a boron and a hydrogen can be the HOMO in a reaction. And more recently, we looked at organometallic reagents, and the HOMO is the carbon metal sigma bond, and that pair of electrons can be donated as a nucleophile. So if we pare all of those examples down to the simplest possible forms, then we see this. We have nucleophiles donate electrons from available high energy orbitals, and they can be represented by one of these four examples. So a lone pair being donated to an electron, a negative charge, which is typically also a lone pair, a double bond, so that's a pi bond acting as a nucleophile, and a sigma bond from an between carbon and an electropositive atom, or between electropositive atom and an electronegative atom. So how do we identify electrophiles? Well, again, there are examples of different types of electrophiles, but they all have in common a lowest unoccupied molecular orbital. A proton is kind of the quintessential electrophile with an empty atomic orbital. A proton, of course, has no electrons, so it has an empty 1s orbital, and that would be then the LUMO, the lowest unoccupied molecular orbital. And that explains, for instance, why hydroxide reacts with protons quite readily to form water. It also explains why water reacts with protons to form hydronium ions. The water is kind of a quintessential electron donor, nucleophile, with a lone pair of electrons. The hydrogen ion acts as an electrophile because it has an accessible, lowest unoccupied molecular orbital. Aluminum and boron compounds are good electrophiles too. Here are two examples. Aluminum chloride, which has a structure it's trivalent with an empty p orbital, or boron compounds. This is boron trifluoride, also trivalent. In here, each case here, they have an empty p orbital. And so species that can donate electrons to these will react with them quite readily. For instance, boron trifluoride is a very reactive gas, but it dissolves readily in diethyl ether where it's more easily handled. And the reason it dissolves readily in diethyl ether is diethyl ether can act as a Lewis base. Boron trifluoride is a Lewis acid. We get the formation of a Lewis acid base complex that's quite stable in solution. So the lone pair from oxygen forms a new sigma bond between the oxygen and the boron. Other species that can act as electrophiles that we're going to examine in more detail down the road in the course are electrophiles where you have a double bond to an electronegative atom. In organic compounds, these are very commonly carbon-oxygen double bonds and carbon-nitrogen double bonds. These are ketones. These are called imines. And in these cases, these are reacted by virtue of a pi star orbital. So the antibond of the pi bond of these. So that LUMO is the pi star orbital. Pi star orbital has this sort of orbital structure, and nucleophiles can donate electrons into that. When you fill the antibond of the pi, you break the pi bond. And so a nucleophile, I showed you this one earlier, such as this, where the electrons in these sigma bonds can donate, can add to carbon, and that causes the rupture of the pi bond, and the electrons in that pi bond go to that electronegative atom. And so this is going to be a pattern of reactivity that we examine in much more detail down the road. Other types of electrophiles that we will encounter are sigma bonds to an electronegative atom. So this is exemplified by things like hydrogen halides, alkyl halides, but also, curiously, by the halogens themselves, things like bromine, so the diatomic halogens. All of these species have relatively low energy LUMOs in the form of sigma star orbitals. And nucleophiles can react with them quite readily. So for instance, ammonia reacts with hydrogen chloride quite readily to form ammonium chloride, where the ammonia acts as a nucleophile, donating its pair of electrons into the sigma star orbital. That causes the sigma bond to break and the pair of electrons in that bond to move to the chlorine. So we get a new sigma bond. In this case, we also produce this chloride ion. So pairing down the electrophiles into their kind of fundamentals, we could have a positive charge representing an empty orbital, here exemplified by proton, but it could be a carbocation, for instance. A neutral molecule with an empty p orbital, boron and aluminum compounds are the most common examples of that. A double bond to an electronegative atom, such as in a carbonyl, and a single bond to an electronegative atom, element of some sort. So this discussion of nucleophiles and electrophiles will inform our look at substitution reactions as we go further into this material. So the bulk of this chapter is going to deal with reactions that have this overall process, where we have a nucleophile, a Lewis base, interacting with a species that will typically have a sigma bond to an electronegative atom. And the result gives rise to an overall substitution where the nucleophilic species replaces that, and this electronegative atom acts as a leaving group. As a heads up, in chapter 8, we're going to see that electronically very similar species react in a different way to give rise to an elimination reaction that looks like this. But for the time being, let's focus on substitution reactions. So what are the types of substitution reactions that we're going to encounter moving forward? And here are a handful of those. And all of these can be described using curved arrow notation and can be described in terms of nucleophile, electrophile, and leaving group. So the first example here at the top, you can see we have hydroxide that is donating its electrons into a sigma star orbital of the carbon iodide bond, and the iodine is leaving as an iodide ion. And so there's this notion of a nucleophile and a leaving group. Second example, we have a sulfide ion. Same thing, it's donating its electrons into a sigma star orbital, in this case a carbon nitrogen sigma star, that breaks the bond, and we form a new sulfur carbon bond and trimethylamine. The third example shows a nitrile. Again, with our curved arrow formalism, we see that we have a donation into that sigma star orbital of the carbon-chlorine bond, and we form a new carbon-carbon bond. In the last two examples, we have fluoride doing a substitution, and our leaving group here is nitrogen. And the last one is a neutral nucleophile in the form of ammonia, adding into the sigma star orbital of the carbon iodide bond, and we produce the methylammonium ion and iodine.